In the previous section, we devoted a large amount of time to understand consumer choice models based on utility functions. These models derived demand functions that are driven by underlying decision problems. In this section, we will focus on the properties of these derived demand functions to further understand the intuition behind their behavior. In this video, we will focus on the effects of the budget or income on demand, and we will think through the intuition about its impact through the utility maximization problem. Remember that the prices and the budgets determine the budget constraint, but they have no direct impact on the preferences, so they don't affect the indifference curves. Therefore, if any of these variables change, the budget constraint moves around, and the derived demands change as a result. If you recall the graph of a budget constraint, its intercepts are determined by the budget or income, y, divided by the price of that good. Let's say a consumer chooses a consumption bundle of beer and wine. Then if we draw a budget constraint of these two goods, with beer on the horizontal axis and wine on the vertical axis, then the vertical intercept of the budget constraint is y divided by the price of wine, and the horizontal intercept of the constraint will be y divided by the price of beer, and the slope will be minus the price of beer over price of wine, the price of the horizontal good over the price of the vertical good. Now, if there is an increase in the budget or income y, how will the budget constraint change? Well, as y increases, both intercepts will increase, but the slope will remain the same. The idea is exactly the same as we discussed different expenditure curves in the previous video about the expenditure minimization problem. So we can imagine that as y increases, the budget constraint shifts out in a parallel way and leads to a different tangent point with a higher indifference curve. And this tangent point corresponds to different demand for beer and wine. We've derived a few Marshallian demand functions for different utility functions. Each demand is usually a function of the exogenous variables. In particular, we saw how they respond to changes in y in our previous exercises. But now, let's think about how this change channels through the model graphically in order to understand the intuition a little bit better. If we zoom into the graph on the right, the top panel illustrates this idea. As the budget or income increases, the budget constraint shifts out from L1 to L2 to L3. Under each budget constraint, the optimal consumption bundle is different at E1 and then E2 and then E3. As the income expands, the optimal consumption bundle moves up to higher and higher indifference curves, from I1 to I2 and then to I3. In this graph, as the optimal consumption bundle moves up, it corresponds to higher and higher demand for beer, which is a horizontal good. So it corresponds to demand of 26.7 initially, moves up to 38.2, and then to 49.1. And for wine, that increases from 2.8 to 4.8, and then to 7.1 for our vertical good, which is wine here. The graph shows three different budget levels, and we can imagine a continuous change in the budget y. As y increases gradually, the budget constraint shifts outward little by little by little. At each stop, there is a new optimal consumption bundle on the constraint. So if we keep track of all of these optimal consumption bundles as the budget constraint shifts outward, we will have a track of optimal consumption bundles. And this track of optimal consumption bundles as the income changes is called the income consumption curve. If all the optimal consumption bundles are interior solutions, as they are now in this graph, then all the points along the income consumption curve satisfy the tangent condition. In fact, you're already very familiar with this curve. When we solve the Lagrangian, all of those equation 4s that we obtained by combining the first two first-order conditions are exactly this curve. For Cobb-Douglas and CES utility functions, these curves are straight lines, where Q2 is a linear function of Q1. In this graph, we're focusing on the changes in the demand of both goods, which were plotted explicitly on the two axes. We have quantity of beer on the horizontal axis and quantity of wine on the vertical axis. A slightly different way to represent this information is to think about how changes in the income/budget level affect the demand curve of one of these goods. In other words, how changes in income alter the relationship between the price of the good and its quantity of demand. Now let's say that the good we're interested in this example is beer. For demand curves, we plot its price on the vertical axis and the quantity on the horizontal axis, just like the first graph above. If you tell me the price of beers is at $12, then as the budget increases, the quantity demanded for beer increases despite its price remains unchanged. First, the demand is at 26.7, and then it increased to 38.2 as the income increases, and then again up to 49.1 as the budget or income increases again. Each value corresponds to the optimal quantities in beer from the graph above. As we have done at the beginning of the class, these curves are plotted from the Marshallian demand function derived from the utility maximization problem above. Each one of these curves represents relationship between the price of beer and quantity demand of beer, holding income level constant. Therefore, as income or budget level changes, we will have different relationships between the price and the quantity, and therefore we'll see different demand curves. As income increases, it is as if all these curves are shifting outward at each and every given price level. In these two graphs, we know changes in income and budget are driving the changes in the quantity demanded, but the budget is always working on the background. One way to explicitly describe this relationship is to plot the budget on the vertical axis and the quantity on the horizontal axis, in order to keep track of the changes in quantity as the budget increases. And this is our third graph below. We have budget on the vertical axis and beer on the horizontal axis. This leads to the green curve that represents the relationship between Y and quantity demanded for beer, while all the variables are kept constant. This curve is called the Engel curve. Just like a demand curve that plots relationship between price and quantity, an Engel curve plots relationship between income/budget and the quantity. Now we see that as Y increases from one value to the next, the quantity demanded for beer increases correspondingly. A key message from all of these graphs is that all these different graphs are just representations of the utility maximization problem and its derived demand from different perspectives. The perspective you would choose just depends on the relationship you'd like to emphasize. Underneath all of these graphs is just the derived demand function. The key information of the Engel curve is the effect of the income/budget on the demand. If we measure this effect in the form of percentage changes, we have the income elasticity of demand. Recall that income elasticity of demand is defined by the percentage change in quantity demanded divided by the percentage change in income or budget. Our operating formula for calculations of the income elasticity of demand is to take a derivative of the quantity demanded with respect to the budget or income, and then multiply by the ratio of income over quantity demanded. We use this notion xi to denote the income elasticity of demand when we introduce it back in the elasticity video. The sign of the income elasticity is determined entirely by the derivative of demand with respect to Y because this ratio is always positive with the positive budget or income and the positive quantity. If the derivative is positive, meaning that QD increases as Y increases, then the elasticity will be positive. On the other hand, if QD decreases as Y increases, then the elasticity is negative. And this sign could go either way for different goods. So the income elasticity of demand may be negative or positive. When Xi is negative, it means that the quantity demanded decreases when Y increases. This is certainly unusual. But you might have learned from a principal class that for certain low quality or inferior goods, consumers choose them when they cannot afford better alternatives. When their income increases, they switch away from these goods and replace them with similar goods with higher quality. One example my previous students liked was single-ply toilet paper, or knockoff fashion. A lot of tech entrepreneurs talk about eating a lot of instant noodles in the early days of startup because of different resource constraints in budget or time. Certainly, as they have more success in their career, those constraints relax to some extent, and they will switch away from instant noodles to have healthier options. On the contrary, for most other goods, consumers typically consume more of them when their budget increases. And we call these goods the normal goods, in contrast to the term inferior goods. Among all the normal goods, the demand for some goods may respond more strongly to changes in the budget. For instance, if my salary were to double, my demand for food, coffee, and gasoline will increase, but they certainly won't double. That's because these are necessities that I need a lot of, and I already consume quite a lot of them. If my income doubles, I won't need double the quantity of these things. And if my income is halved, I won't be able to cut these consumptions by half. So the percentage response in demand for these goods are likely to be less than the percentage change in my budget. In other words, the income elasticity is likely to be inelastic. Whereas on the other hand, some goods are luxury goods. They're nice to have if we have the budget for them, but we certainly don't need them if the budget is very tight. So the percentage response in their demand is likely to be more than proportional to a 1% increase in income. If my income doubles, I suddenly start to consume these things. And if my income halves, I will stop consuming all of them altogether in order to pay for the necessities in life. You can think about fancy food, fancy coffee, expensive hotels for travel, or designer clothing, etc., etc. And certainly, a good isn't necessarily an inferior good or normal good for everyone. For instance, charitable donations may be one person's luxury good, but another's necessity. It all depends on the preferences of the consumer. From the perspective of our utility maximization model, the preferences shape the indifference curves, which then determines how the income consumption curve moves as a budget constraint shifts out. Speaking of knockoffs, a study of Basman and Dapkin in 2006 estimates the income elasticity of pirated goods. They found an income elasticity of negative 0.25, meaning that as income increases by 1%, the demand for consumption of pirated goods decreases by 0.25%. So it is inelastic, but the demand decreases nonetheless. In other words, pirated goods in the context they study is an inferior good, which is not surprising. Some economists use the utility maximization problem to think about decisions beyond common sense consumption. If you think of the number of children a family decides to raise as a consumption choice for a good that is chosen in conjunction with all other goods in life, then you can come up with a demand function for the number of children. That is determined by the cost of raising children and income, etc., etc. Many economists study this topic, and Gounet, 2011, provides a survey of this literature at that point. The survey reported that most studies finds an income elasticity that is slightly negative, but very close to zero. This means that on average, income has almost no impact on the number of children a family decides to raise. If you're into food and drinks, you might like health economics and agricultural economics. Both fields in economics pay a lot of attention to these topics. For instance, Kim and Lee, 2011, estimated the demand for fast food restaurants. They found an income elasticity that is positive when the consumer's income is below $60,000, but the elasticity becomes negative when income is above that. This means that fast food is a normal good for lower income households, but an inferior good for higher income households. This makes intuitive sense. If someone is very poor, then they probably consume low-cost, high-energy frozen food that is unhealthy and untasty. As other income increases, they're likely to switch to fast food, which are still not healthy, but probably a little bit better, and also probably taste a little bit better than frozen alternatives. This leads to a positive income elasticity. As the income increases further, their budget starts to allow for healthier and more fresh foods. Then they are likely to switch away from fast foods, leading to a negative income elasticity. On the graph here, you can see that it is exactly because of the way these indifference curves are located. As the budget constraint shifts out, the tangent point first shifts upwards towards the right, but then start to shift towards the left. So the quantity demanded first increase as the income increases, but then start to decrease as the income increases further. If we plot the angle curve for this case, we would have a backward bending angle curve, which illustrates the same idea. As income increases, quantity demanded increases, but beyond a certain income level of $60,000, the elasticity becomes negative, the demand starts to decrease as the income increases further, leading to this backward bending angle curve. An important takeaway from this example is that the income elasticity of demand is usually not fixed for all income levels. A good may be an inferior good to some, while being a normal good for others. Economists use the term heterogeneity to refer to these important differences underneath the average. It is important to keep in mind about these nuances and differences across different groups, especially when we interpret any average statistics. In the statistics and econometrics classes, you will learn about the techniques to identify these rich heterogeneities from data. We see in this graph that one of the two goods that the consumer is choosing can be an inferior good. Then it is natural to ask, is it actually possible for both goods to be inferior simultaneously? Well, the answer is no. The intuition is actually quite simple. Let's look at this graph on the right-hand side. Suppose that originally the budget constraint is this dark blue curve, and the optimal consumption bundle is at the red point here. Now, as the income/budget increases, the budget constraint shifts outward to this lighter blue curve. We saw in the previous graph that it is the particular shape of the indifference curve that leads to the inferior good outcome for the horizontal good, which was the fast food in that case. So, is it possible for us to find some special looking indifference curves that render both goods inferior? Well, it turns out the answer is no. The reason lies in our intuition that a utility maximizing consumption bundle must lie on the budget constraint. Although where the optimal consumption bundle eventually lies will depend on the shape and location of the indifference curve, but we know it will definitely be on the budget constraint for sure. Now suppose that both goods are inferior. then what it would mean is that the consumption decreases for both goods relative to the original consumption bundle at the red point, even though the budget constraint is now shifting out. This would mean that the new optimal consumption bundle will actually lie below this red point, to the left of Q1 star and below Q2 star. Then it will mean that certainly the new consumption bundle wouldn't be on the budget constraints. And that certainly is a contradiction to something we know has to hold for true. And therefore it is impossible for both goods to be inferior. To think about this slightly differently, regardless of where the new optimal consumption bundle lands on the new budget constraint, at most one of these goods can be inferior. We can reference the levels of the optimal consumption bundle from the starting point and cut the new budget constraint into 3 different sections. In the upper section, all the bundles on the budget constraint will have less Q1 comparing to the original red point, but have more Q2. In other words, if the optimal consumption bundle lands anywhere in this section, then good 1 will be an inferior good, whereas good 2 will be a normal good. And similarly, down below in this section, wherever the optimal consumption bundle lands, good 2 will be inferior, but good 1 will be a normal good. And if the optimal consumption bundle lands anywhere in this section in the middle, then both goods will be normal goods because the quantities will increase relative to the original red point. Therefore, we have exhausted all the possible landing points for the new consumption bundle, and nowhere you'll be able to find a point where both goods are inferior. It turns out that this intuition can be generalized to derive a very precise expression related to the income elasticity of demand. In this expression, Xi1 is the income elasticity of demand for good 1, and Xi2 is the income elasticity of demand for good 2. What this expression says is that if we add up these two income elasticities with some proper weights of theta 1 and theta 2, then they will actually add up to be 1. So what are these weights, theta 1 and theta 2? Well, they have very intuitive interpretations. They are just the share of income or budget spent on good 1 and good 2 respectively. So if a consumer spends 20% of the budget on good 1 and 80% of the budget on good 2, then theta 1 will be 0.2 and theta 2 will be 0.8. These two weights will add up to 1 by themselves, but the expression here says something different. It says that the sum of the income elasticity of demands weighted by their expenditure shares will be 1. Note that such a very specific relationship actually holds regardless of the utility function, the income level, or the prices. And now let's try to prove this expression. Surprisingly, the proof only takes a few lines. So just like our previous intuition, the key for the proof is that the optimal consumption bundle must lie on the budget constraint. Therefore, the optimal quantities Q1 star and Q2 star must satisfy our expression for the budget constraint. Next, just like the previous intuition, we consider an increase in the budget. So imagine the budget constraint now shifts out slightly. We know that before and after an increase in Y, the optimal consumption bundles are going to respond. And they will always be on the budget constraint. So as the constraint shifts out, these quantities will actually move with the constraint. And we'll want to use algebra to help us keep track of how the Q stars move as Y increases. To do this, we're going to take derivative with respect to the budget constraint on both sides of the equation, while recognizing that both q1 star and q2 star are functions of y. You can think about the Marshallian demand function from Cobb-Douglas or CS utility functions. They're all functions of y. Because the prices are exogenous, so P1 and P2 don't vary when y changes. But Q1 star and Q2 star will respond to the changes in y. We don't know exactly by how much they will change, but they would be measured by the derivatives of the demand functions with respect to y. On the other side of the equation, the derivative of y with respect to y is just 1. So there we have this equation. This step is the key to the entire proof. What's left over is just one trick to drive us home. What we want to do here is to rewrite these two derivatives into the form of elasticities. Remember that income elasticity of demand is the product of the derivative of quantity with respect to income, which we already have, multiplied by the ratio of income to Q, which we don't have in this equation we just derived. So we will need the ratio here. The trick is to multiply the needed ratio and its own reciprocal at the same time. So we're effectively multiplying by 1, which has no substantive effect on the equation. Specifically, we will need y over q1 star here, and we'll need y over q2 star here. So we can write this as income elasticity for good 2. And of course, we'll multiply by the reciprocal of this made-up ratio. And now we realize that we have the income elasticity of demand for good 1, which is xi1, and we have the income elasticity of demand for good 2, which is xi2. Now what we can do is we can pack up the xi1 and xi2s, and we still have some leftover stuff. In the first term, we're going to have P1 times Q1 star over y. In the second term, we're going to have P2 times Q2 star over y. And the sum of these things is equal to 1. So rewriting these expressions down, pulling out xi1 and xi2, what we have is P1 times Q1 star over y times xi1 plus that times xi2 is equal to 1. But hey, if you stare at these expressions long enough, you realize that the numerator is the expenditure on good 1, and the bottom is the budget. In other words, this ratio is exactly the expenditure share in income, which is exactly the definition of theta 1. And similarly, theta 2 here. And there we have it. This is the expression we want to prove, which is theta 1 times xi1 plus theta 2 times xi2 is equal to 1. And we're done. Notice that this proof does not rely on the form of the utility function at all. So it works for all Marshallian demand. The trick we used above to write derivatives into elasticities is a very common trick that we will use repeatedly later on. So it is important to understand how it works. One implication of this expression is exactly our previous remark, which says that at least some good in the consumption bundle must be a normal good. But why does this expression give you that result? The upcoming argument is called a proof of contradiction. Let's first suppose that both goods are inferior. Then what's going to happen is that their income elasticities are both negative. As a result, their weighted sum must be a negative value. But then it becomes a contradiction to this expression we just proved, which we know has to be true. Therefore, our starting position, which is the presumption that we suppose both goods are inferior, must be untrue, which shows that it is impossible that we have both goods to be inferior at the same time. Beyond this theoretical result, this expression can also be a very useful tool to help us make conjectures with very little data, And let's look at an example now. Let's suppose that a consumer only purchases 2 goods. He spends 40% of budget or income on good 1, and the income elasticity for that good is Xi1 equal to 0.3. What is the income elasticity for the other good? Xi2. How do we answer this question? Well, because it involves consumption share and income elasticity, let's try to use our previous formula. To do that, we can parse out from the question that theta 1 is 0.4 and Xi1 is 0.3. Moreover, from the formula, we know that theta 2 times Xi2 added to theta 1 times Xi1 will be 1. So if we can somehow figure out what is theta 2, then we can back out Xi2 from the formula. But do we know theta 2 from the question? Yes, of course. With 2 goods, the expenditure share of good 2 and good 1 must add up to 1. So if good 1 takes 40% of the budget or income, then good 2 must take 60%. Now in our formula, we already have theta 1, which is 0.4. We have Xi1, which is 0.3. We figured out theta 2 from theta 1, which is 1 minus theta 1, which is 0.6. So now we can just solve for Xi2. We can rewrite this equation a little bit by moving theta 1 and Xi1 to the other side of the equality, and then divide both sides by theta 2, which is 1 minus theta 1. And there we have this expression. So now plugging in these values, we can figure out the value for Xi2, which is approximately 1.47. To show how this formula can be useful with even less data, let's look at a different example in the textbook. In this question, it says, in Beijing, China, the average consumer spent 60% of income on food in 1983. That was a time when China was still very poor, and residents in Beijing still have very low income level. If we assume that the food consumption is a necessity, then what is the possible range of income elasticity for all other goods at this time? To use our framework, let's think of food as good 1 and think of all other goods as a big bundle of good 2. For the question, we learned that theta 1, the expenditure on food, is taking 60% of income. And we also know that food is a necessity by assumption, which means that the income elasticity of demand for food is going to be somewhere between 0 and 1. Just like the previous question, we can back out theta 2 from theta 1, which is 1 minus 0.6, that is 0.4 here. What's different now is that we don't have a precise value of Xi1 anymore, and we only know it's somewhere between 0 and 1. Now, if we take a look at this formula, and also the one we rewrote in the previous question, we noticed that Xi2 is actually a linear function of Xi1. It only appears on the numerator with a negative sign in the front, while theta 1 is completely fixed. Although we don't know a particular value of Xi1, but we know the bounds for it. With a greater Xi1, we're subtracting a bigger and bigger number from 1, leading to a smaller and smaller value for Xi2. On the contrary, with a smaller Xi1, then we're subtracting a smaller number from 1, leading to a greater value of Xi2. In other words, Xi2 is decreasing in Xi1, and therefore, if we plot Xi2 as a function of Xi1, it's going to be a downward sloping curve, where as Xi1 takes a value of 0, Xi2 will reach its highest point, whereas as Xi1 increases, we're subtracting a bigger and bigger value from 1, so Xi2 keeps decreasing. And as Xi1 reaches the value of 1, which is our upper bound for Xi1, that will correspond to the lowest possible value for Xi2 within this range. as of all of these xi1s that's running between 0 and 1, they're going to correspond to values of xi2 that runs between these two extreme values that are reached at the upper and lower bound of xi1. Once we understand this relationship, it just remains to calculate the bounds of xi2 as xi1 varies between 0 and 1. So we can just use this expression we derived and plug in the two extreme values of xi1. We found that xi2 will take the value of 1 when xi1 takes a value of 1, and xi2 will take a value of 2.5, a much higher value, when xi1 takes the lower bound value of 0. And of course, from our previous argument, we know that xi2 is going to lie somewhere between 1 and 2.5, as xi1 runs between 0 and 1. The power of this example is that it shows how we're able to make an educated guess and narrow down to a very small range of values with very limited data. Essentially, all we needed is the consumption share between categories of goods and an assumption about necessity. With more data, certainly we would be able to make more precise estimates using statistical methods. But this example demonstrates that a theoretical framework can help us make inferences when data is very scarce, or to provide a preliminary estimate before engaging in detailed data work.